Chapter 11, Working with Quadratic Functions. In this first screencast for this chapter, we will consider an introductory example to motivate this topic. So let's look at example 11.1. Did you know that people living in the United States use roughly 80 to 100 gallons of water every day? In this example, we consider how water consumption in a small town might change over time. So let's start by looking at part A. Suppose that the population of our town is represented by the variable P, and that annual per capita water consumption in the town is represented by the variable C. Write down an equation that will estimate W, the total annual water consumption in the town. Well, before we try and write down an equation, let's make sure we're clear on what everything in this problem is referring to. First of all, there's some language here. Annual per capita water consumption. So first of all, the term per capita. What does per capita mean? Well, per capita is another way of saying per person. So we have annual per capita water consumption represented by this variable C. So in other words, C represents water consumption and this is per person, and this is annual, so it is also per year. So this is what annual per capita water consumption means. Now, we're told that P represents the population of the town. So P equals population of town. And finally, we're told that W is the total annual water consumption for the town. So W equals water consumption of town, and this is annual, so that makes this per year. Okay, so these are the three quantities that are referred to in this problem, and our goal is to write down an equation that will estimate W. Okay, well, W is the water consumption for the whole town for a year. If you were going to calculate how much water was consumed by an entire town over a year, perhaps the easiest way of doing it is to calculate how much water one person, or a typical person, or an average person, consumed each year, and then multiply by how many people there are in the town. So you multiply the water consumed by a person over a year by how many people are in the town, and that should give you an estimate for the total amount of water consumed by the whole town. So our resulting equation would be W equals C times P. Okay, we will come back and use this equation later in a follow-up part of this example, so don't forget about that equation. So let's move on now to part B. So, part B. Let's assume that the population of the town is growing linearly over time. In the year 2000, the population was 3,400, and in 2010, the population reached 5,000. Determine an equation that will estimate P, the size of the population. Remember, that's the same P as we had up here. That will estimate P, the size of the population, T years after the year 2000. So again, there's an awful lot in this problem. Before we set out to find an equation that will estimate P, let's try and organize the information that we've been given. So let's start by just making a table. So we're given information in a couple of years. We're given information in the year 2000, and we're given information in the year 2010. Ultimately, our goal is to write an equation that relates two variables, a variable t, which represents time in years after the year 2000, and p, the size of the population. So let's fill in numbers for these two variables. Well, in the year 2000, t should equal 0 because we're talking about 0 years after the year 2000. In the year 2000, the population was 3,400 people. Now, in the year 2010, we're talking about 10 years after the year 2000, so t is 10, and in the year 2010, the population reaches 5,000. So now that we've got a table that organizes all of this information, I think we can even go a step further and write down a graph that would describe the relationship between the variables t and p. So I can make two axes like this. Our goal is to estimate p. So this is going to be the output variable. T is our input variable. So t will appear on the horizontal axis and p will appear on the vertical axis. Make some tick marks here. So recall that when t is 0, this refers to the year 2000. So I'm going to mark 2 years later, 4 years later, 6 years later, 8 years later, and 10 years later. So 10 years after 2000, that would put us in the year 2010. For population values, notice that they range between 3,000 and 5,000. So I'm going to make a tick mark right here for 3,000, a tick mark here for 4,000, and one here for 5,000. And now I think we can plot coordinates of 2 points from up here. So when t is 0, p is 3,400. That would be approximately here. And when t is 10, p is 5,000. That would put us approximately here. And we're told that the population is growing linearly over time, so that would mean I would connect the 2 points with a straight line. So we have a table representation of our data, and we have drawn a graph of the equation or the function we are trying to create. The last thing we need to do now is just write down the actual equation. It's going to be a linear function, so that means it should have the form y equals mx plus b. But in this problem, we don't have variables x and y. We have variables t and p. P is playing the role of the y, and t is playing the role of the x, because t is the independent variable and p is the dependent variable. Next, we need to find m, which would be the slope of the line. M is going to be the change in the output divided by the change in the input. Well, the change in output, that's the change in population. The change in input, that's the change in time. We can calculate these two changes by going back up to our table here. We can see that from the year 2000 to the year 2010, the population grew by 1,600. So that is the change in P, 1,600 people. And if we go back to our table and look at the t variable, we can see that t increased by 10 years. So we can write our change in t as 10 years. When we divide, we get 160 people per year. So that's how many new people are added to this population every year. The other thing we have to calculate is b for this equation. B, if you recall, is the vertical intercept of your function. And in this case, B is located right here. We can see the value on the graph, and if we go up to our table, we can see what that point is, and right here, the 3,400 gives us the location of that vertical intercept. So B is actually 3,400. So the equation that describes the population growth for this town is P equals 160T plus 3,400. And we will use this equation again in a later part of this example. So before we move on, though, it's worth pointing out that the p-value up here in this equation is the same as the p here. Ultimately, we're going to substitute our formula for p right here into that spot. So keep that in mind as we move forward. Okay, now let's have a look at part C. Let's assume that per capita water consumption, and again remember, per capita means per person. Let's assume per capita water consumption in the town each year has been decreasing linearly, with 37,000 gallons per person for the year 2000 and 29,000 gallons per person for the year 2010. Now those are annual numbers. If you did a unit conversion, you would see that this is a decrease of about 100 gallons per day per person down to about 80 gallons per day per person. Determine an equation that will estimate C, the annual per capita water consumption, T years after 2000. Okay, this problem is very, very similar to part B. So let's start this problem the same way we started part B. We're given a fair amount of numerical information. Let's first of all organize it on a table. So we're given information in certain years. In particular, we're given information in the year 2000 and information in the year 2010. We're being asked to write down an equation that relates two variables, T and C. And just like in part B, the variable T represents the number of years after the year 2000. So in the year 2000, T has the value 0, and in the year 2010, T has the value 10. C represents the annual per capita water consumption. That would be gallons per person per year, really. So in the year 2000, we're told that the value of C is 37,000 gallons. And this is per person. And it's really per year also. And in the year 2010, the per capita consumption dropped to 29,000 gallons. Per person. And again, this is per year also. We could also draw a graph, a very rough graph, of what this function ought to look like. We have limited space here, but I think I can squeeze in a small graph. Just as in the last example, T is our independent variable, or our input. In this case, C, the quantity we're trying to estimate, that's our output. So we can make some tick marks as we did before. Let's say this is 2 years, 4 years, 6 years, 8 years, and 10 years out. And on our vertical axis, we need to mark a couple of values. Notice at T equals 0, the per capita consumption is 37,000 gallons. I'm going to mark 37,000 gallons. I'm going to mark that right there. So that's going to be 37,000 gallons right there. And the consumption over the 10 years, it drops down to 29,000 gallons. So when T is 10, let's just assume right here is 29,000 gallons. So when T is 10, we've dropped down here to 29,000 gallons. So when we draw our graph, it's going to look something like that. So this was, again, just a very rough sketch of what the graph would look like. Now that we've got a table showing our information and we can see what the graph of this linear function looks like, I think we're in a good position to write down an equation for the relationship between T and C. This is a linear function, therefore it must have the form y equals mx plus b. Now there are no variables x and y here. C is playing the role of y, T is playing the role of x. We need to determine the values of the slope m and b. So let's start with the slope. M is the change in output divided by the change in input. In this case, that's the change in C divided by the change in T. If we look at our table, we can see that the value of C dropped by 800 gallons, or sorry, 8,000 gallons. So we've got a drop of 8,000 gallons. Meanwhile, if we look at the value of T, we can see T grew by 10 years. So we're going to divide by 10 years. So when we perform the division, we arrive at negative 800 gallons per year. And actually, the numerator is gallons per person. So our final answer is minus 800 gallons per year per person. That's M. Now, to calculate B, that's our vertical intercept, and we can see that from the graph. The vertical intercept is our initial amount, which is 37,000. So 37,000 gallons per person per year. So our final equation is C equals M, that would be minus 800 times T plus 37,000. So that is our equation that relates C and T. Okay, so now let's move on and look at part D. Assuming that both the population and the per capita consumption are changing linearly, write down an equation that will estimate W, the total gallons of water consumed in the town T years after the year 2000. Okay, we talked about this earlier in the screencast. In part A, we set up the following equation. We said that W was equal to C times P, where C was the per capita water consumption, in other words, the per person water consumption, and P was the population of our town. In part B of this example, we created a function for the population, and in part C, right above here, we created a function that represented the C value. So now we can fill in the C and the P with their respective functions. In place of C, I'll write down how it is growing. Negative 800T plus 37,000, and in place of P, I'll write down the function we created that describes the growth of the population, namely 160T plus 3,400. So W here ends up being the product of two linear functions. One linear function describing the decrease in water consumption per person, and another linear function describing the increasing population. Let's multiply these two functions together using the distributive property. We'll simplify and then we'll write down the resulting equation. Okay, if we are going to multiply these two linear factors together using the distributive property, we need to make sure that we multiply each term from this first expression by each term in the second expression. We've done this before back in chapter 6. So let's do it slowly here. We'll multiply the negative 800T by the 160T from the other expression. Then we'll multiply the negative 800T by the 3,400 in the second expression. Next we'll multiply the 37,000 from the first expression by the 160T in the second expression. And lastly, we'll multiply the 37,000 from the first expression by the 3,400 in the second expression. So I believe we have multiplied each term from the first expression by each term in the second expression. Now we have to simplify. Okay, so we have W equals, first we multiply the negative 800 by 160. That will give us a negative 128,000. Notice that we're also multiplying T times T, so that will give us t squared. Next we multiply negative 800 by 3,400. That will give us a negative 2,720,000, and there's also a t there. Next we'll multiply the 37,000 by the 160. That will give us 5,920,000 t. And finally we multiply the 37,000 by the 3,400. And that will give us 125,800,000. Almost done. So now we just need to combine like terms. There are two like terms here. So I'm just going to copy down our first term. When we combine the like terms, we end up with 3,200,000 t, and then we have our last term, 125,800,000. So the values in this function are really quite large, and you might be wondering why we have such large values in this resulting function. Well, remember what W represents. W represents the annual water consumption for a whole town in gallons. So when we substitute in different values for t, different years, this equation is going to be calculating a very large number of gallons. So it's not surprising that you're seeing large numerical values showing up in the equation. Okay, let's go to part E. Here we are, part E. When both the population and the per capita water consumption change linearly, the total amount of water consumed annually does not grow or decrease linearly over time. Explain why you know this. Okay, well, let's look at the equation that we ended up with for W. If W changed linearly over time, then this equation would have to have the form y equals mx plus b, or more specifically, it would have to have a form like this, W equals mt plus b. So as you compare this equation with this equation, you ask, do they have the same form? This equation is a number times t plus another number. But notice in this equation up above, we do have a term that is a number times t plus a number. So this part here kind of fits this, but there's this extra term that involves t squared. Linear functions, linear equations never involve the input variable being squared. Linear equations never have the input variable being squared. So the presence of this term right here means that W cannot be changing linearly. So what is the precise form that the W equation has? Well, if we look at our equation for W, the one we really have, it looks like this. W equals, and then there's a number times t squared. So I might write that this way, A times t squared, where A is this negative 128,000 plus Now there's another term here that is a number times t. Well, I could write that as b times t, where b is the 3,200,000 plus there's a final number in the equation. It's not multiplied by any t value, so I'll just call it c, where c is the 125,800,000. So the equation we really have for W, this equation right here, it's not linear. It does not have this form. Instead, it has a form that looks like this, where you have a term that involves t squared. And that is why we're talking about this example in the context of quadratic functions. Quadratic functions have forms like this. Okay, let's do a brief recap before we move on to part F. We've created a function that will estimate the town's total water consumption over the course of a year, which we're calling W. We calculated this function by multiplying each person's water consumption over the course of the year, which we're calling C, that's the per capita water consumption. We're multiplying that by how many people are in the town, which is P, the town's population. We assumed that each person's water consumption was decreasing linearly, and that gave us this formula. So this represents per capita water consumption, or each person's water consumption over a year. We multiplied that by a function representing the increasing population of the town. We created a linear function representing that increase. T represents the number of years since the year 2000. We used the distributed property to multiply these two linear factors together, and we arrived at a formula which will calculate the town's total water consumption over the course of a year. Now let's move on to part F. Complete the following input-output table for the function above. Express your outputs using scientific notation. As we said previously, we expect this function to produce some very large numerical outputs because we're calculating the total number of gallons that a whole town uses over the course of a year. So it makes sense that we would want to express our outputs using function notation. Okay, let's suppose t is 0. Remember, that would be the year 2000. If we substitute 0 into our function in place of t, we will get a 0 here, a 0 here, and we will have this constant. So we will have 0 plus 0 equal, or plus 125,800,000. So our answer will be 125,800,000. Writing that with scientific notation, we get 1.258 times 10 to the 8. And this is gallons per year. Okay, now let's look at the next entry. Now t is 10, so we substitute 10 here for t, and we substitute 10 here. At this point, you'll want to break out your calculator. When you calculate the output of this function when t is 10, you arrive at 145 million, which we would write in scientific notation as 1.45 times 10 to the 8. And again, this is gallons per year. Similarly, we substitute 20, 30, and 40 into our function in place of t, and we calculate the outputs. In the case of 20, you will arrive at 1.1 386 times 10 to the 8 and 1.066 times 10 to the 8 and 4.9 times 10 to the 7. All of these, just like the top one here, represent a certain number of gallons each year. Let's look at part G. On the axes provided below, carefully draw a graph showing the annual water consumption in this town. Connect the points you plot with a smooth curve. So basically what we're trying to do is get a feel for what the graph of this function that we've created looks like. We've got some points here that we can plot. So let's do that. First of all, let's plot the first input-output pair associated with t equals 0. The output is 1.258 times 10 to the 8. So when t is 0, we have an output that is approximately right here. When t is 10, we have an output that is approximately here. When t is 20, we have an output that's right around there. When t is 30, we have an output right around there. And when t is 40, we have an output right about there. And I think you can see a trend in the points. And if we connect the points with a smooth curve, it looks something like this. So you can see W is not graphing a line. W is not representing a linear function. Okay, let's look at part H. What is the predicted total annual water consumption for the town in the year 2025? Well, there's two ways we could go about answering this question. First of all, let's just look at the graph. In the year 2025, what value does t have? Well, remember, t represents the number of years since the year 2000. So in the year 2025, we're talking about 25 years later. So t is 25. So if I go to the graph and I start in the 25th year, t is 25, if I go up to the curve, I get a point right about there. And if I go over to the vertical number line, it really looks like we are at the same water consumption that we were at back in the year 2000 when t was 0. So we may not be exactly at the same level of consumption, but it appears that we're close. So what we can do to figure out the predicted value of the total consumption is to go back to our equation. So the equation for the function, we figured it out up here. So if we substitute 25 in for t, we should be able to arrive at an estimate for consumption in the year 2025. So let's do that. So W would equal negative 128,000 times 25 squared plus 3,200,000 times 25 plus 125,800,000 We work that out, and we come up with 1.258 times 10 to the 8th, and this would be gallons over the course of that year. We can check to see if the value we arrived at, namely this value, agrees with the value we got in the year 2000. We calculated that value earlier. So if we look up here in the year 2000, which corresponds to t equals 0, we can see we did arrive at a consumption value that is identical to the value we just got in the year 2025. Let's look at part I. So why do you think the graph increases initially and then decreases? Well, is that true? So if we look at the graph we obtained, you do see an initial increase followed by a decrease. What could possibly cause this? Well, if you recall, let's go back all the way up here and think about how W was created. W, remember, is a product of the per capita consumption and the population of the town. Each person's consumption was decreasing or assumed to decrease at a constant rate. Meanwhile, the population was growing at a constant rate. What you are seeing in this picture is the interplay of two competing factors: increasing population growth at a constant rate, and each person's water consumption decreasing also at a constant rate. The last example motivates the following definition. A quadratic function is a function formed from multiplying together two linear functions. In our last example, one of the linear functions was population growth, the other linear function was per capita water consumption. The two linear functions are referred to as linear factors. Using the distributive property to multiply the linear factors, every quadratic function can be expressed in the standard form. So a quadratic function is a function that has this basic form. This looks very similar to our equation for W, the total water consumption in that town. In that example, we had T in place of the X that you're seeing here. Here, X represents the independent variable, or the input, Y represents the dependent variable, or the output, and the letters A, B, and C represent known real numbers. In our last example, A had the value -128,000, B had the value 3,200,000, and C had the value 125,800,000.